We present a method for multiplexing and demultiplexing several illumination conditions from a single shot of the scene. In this video, we will introduce our multiplexing and demultiplexing algorithms, and show results and applications of our approach. Various illumination can not only influence our perception, but also reveal different information of the scene. Several computer vision and graphics algorithms such as image-based relighting, photometric stereo, and multi-flash photography all build on this observation. Traditionally, multiple images need to be taken, each under a different illumination. This method works well for still scenes, but requires robust motion compensation algorithms to cope with dynamic scenes. To lift restrictions on dynamic scenes, we propose a method to multiplex all available illuminations into a single image, and then separate the individual lighting conditions from it. In our setting, we use a camera to record the scene, and then multiple projectors as light sources. In order to multiplex all lighting conditions into one shot, we use a computational coding scheme to encode each illumination. In the coding process, we pixel-wise multiply a structured light coding pattern with illumination at the projector imaging plane to uniquely encode each illuminant. However, for most structured light patterns, scene geometry can introduce variations in frequency and phase of the projected patterns, which makes decoding difficult. To overcome this, we observe that in the dual imaging pair formed by the camera and the projector, an epipolar line projected by the projector will be imaged as the corresponding epipolar line in the camera, regardless of the scene. Thus, if we project a fan-like sinusoidal pattern centered in the projector epipole, the reflected pattern in the camera will also be a fan-like sinusoidal pattern centered in the camera epipole. The captured coding pattern does not depend on the scene geometry and is fully computable. We can choose an illumination coding pattern such that after rectification, the reflected coding pattern in the image will be all horizontal and have a constant spatial frequency. We superimpose all encoded illumination into one single shot. After rectifying the captured image, we can then use frequency analysis to demultiplex each illumination. In the rectified image, we have a horizontal sinusoidal pattern and several other fan-like sinusoidal patterns all present. Each sinusoidal pattern is amplitude modulated by the scene's response to the uncoded illumination. We are interested in recovering the local amplitude of the horizontal sinusoid. For a local neighborhood, we assume that the amplitudes and frequencies of all sinusoids are constant. Since the horizontal sinusoid has a no constant frequency, we then use the short-time Fourier transform to extract the amplitude of the sinusoid of interest. We use the sliding window technique for the whole image. The final resulting images will have a resolution inverse proportional to the window size. Now we show the application of our method on video data. The scene is illuminated by 3 projectors. After coding all 3 illuminations and superimposing them onto the scene, the captured video is shown here. From this video, we can demultiplex the 3 light sources. The demultiplexed images can then be used in single-shot image-based relighting, multi-flash imaging, and photometric stereo.